Okay, these are homework problems from last week. Um, what was last week? 18. There's a few of these I'm going to end up skipping because they have to do with angular momentum and we didn't get to that. So we'll save those for after spring break, but I'll just mention that when we come to those. So, okay. First one, we've got spheres that are attached to light rods and they can move in circles as shown below. So we want to rank the torque values about the center of the circles. Okay, so this is the rod and this is the sphere, and they're moving in these circles. So they're rotating. So there's a torque acting on them to get them to rotate. And we want to rank torque values. So remember, torque is radius times force times the sine of the angle between them. All of these are perpendicular. So this is going to be 1. I don't have to worry about that. So I'm just going to look at the radius and the force for each of these. Okay, so number 1, I've got just radius times force, R and F. Number 2, I've got R times 2F. That's what they give me. Number 3, I've got 2R times F. Number 4, I've got 2R times 2F, or 4RF. Okay. So if I rank smallest to largest, okay, 1 is going to be my smallest because it's just R times F. Okay. It's less than 2 and 3 are actually equal. They're both 2RF. So 2 equals 3. And then 4 is the greatest because it's 4RF. So here, this is a little cleaner than some of the other times we've done this with other equations in the past, because you don't have to square anything. You're not squaring radius or force. So, okay, we got a seesaw. 2 children are trying to get a seesaw to balance. I'm just going to put a line here so that we can separate these two problems. So, seesaw. We got 2 children on it. We got 1 on one end, 1 on the other. They're trying to get it to balance. So Sam is 45 kilogram mass. He's sitting 2.5 away from the center. Where will Stephanie, whose mass is 30, need to sit? Okay. So this is a static equilibrium or a balanced torque problem. This is my pivot point. So these two are going to rotate around the pivot point. One is going to rotate clockwise. The other is going to rotate counterclockwise, depending on where they sit. So if they want to balance it, the forces and radius on one side have to equal the forces and radius on the other side, the torque combinations. We need a counterclockwise torque equals a clockwise torque. Okay. So counterclockwise, I'm just going to say this is Sam. If Sam sits here on this side of the seesaw, he's going to push it down, so it's going to rotate in a counterclockwise manner. So Sam is so we're going to use radius of Sam times force of Sam's got to equal radius of Stephanie times force of Stephanie. Okay. So Sam is 2.5 away from the center, and he's 45 kilograms. To get his force is his force of gravity. Okay, but it's going to be mg for each of these kids. G is going to cancel, but I'll go ahead and write it. We need R of Stephanie. We need her distance that she needs to sit from this pivot point, and her mass is 30. And we're going to multiply that by G, so G is going to cancel. So we're going to end up with 2.5 times 45 divided by 30 should give us where Stephanie needs to sit. And I got to find my calculator. Okay, there it is. So 2.5 times 45 equals, divided by 30, 3.75. So Stephanie has to sit 3.75 from the pivot point to balance the seesaw. And there's more we could say about their placement. Like Sam, is sitting closer to the center of the seesaw than Stephanie. Their masses are different. So there's like a combination of balancing that's occurring here, so that we can get them to get the seesaw to balance. All right, we got a pulley here. What's the net torque about the axle and the pulley? So this pulley, it's got like an axis of rotation here. They give us a diameter of the pulley and some weights, I guess, on either side that are pulling on the pulley. Okay. So we're going to do a net torque here. We're going to have to get our clockwise torque plus our counterclockwise torque. This is just like net force. Like if we added, say, applied force and force of friction for something on a table, you end up subtracting one from the other because they're in opposite directions. We're going to do that here. So let's see, this mass, as it pulls on the pulley is going to move around in a clockwise manner. So this is actually going to be my negative. Okay. So I'm going to have minus 30 as my force, times my radius is 4 centimeters. My diameter is 4 centimeters, so my radius is 2, and I got to convert that to meters. So I'm going to have 0.02. Okay. Plus my counterclockwise is this one. When this one pulls down, it's going to move in a counterclockwise method, and that's positive. So 20, again, times 0.02 for my radius. Okay. And that's just me taking this diameter, divide by 2, and then converting that to meters. So I end up with 30 times 0.02 is 0.6, and that's a minus. And 20 times 0.02 is 0.4. So I end up with a minus 0.2 newtons times meters. And note the minus. Okay, so my net torque on this is in a CW clockwise direction. Let's see, I might get through one more on this page. So here is a person using a wrench. Remember I showed you all a wrench in class. They're having to tighten spark plugs on their car, so they've got to pull on this wrench. And they have to pull at an angle because they can't get all the way underneath the hood of the car to the part that they need to wrench on. So they got to pull at an angle of 120 degrees. With what force must they pull? Okay. And they've got to tighten it to a torque of 38 newtons per meter. Maybe that's like the specification that comes from the manufacturer or whatever. Okay. So we know that our torque we want is 38 newtons per meter. We know our radius is the length of the wrench because it's going to pull. This is the pivot point. It's going to rotate around that pivot point. Okay. We know that that's 25 centimeters or 0.25 meters. And we've got an angle here. Okay. We've got an angle of 120 degrees. So we're going to use torque equals R times F times sine of our angle. And this, I try to use phi just to make it different from theta, but you might see theta as well. In this specific equation for torque, this angle refers to the angle between the radius and the force. So it's just a really specific angle in this scenario or in this problem type. So I'm going to have 0.25 times, let's see, 38 equals 0.25 times F times the sine of 120. Okay. So let's do sine of 120. 0.866 times 0.25 gives me 0.2165. I'm just kind of doing some reducing here. 38 equals 0.2165 times F, and then I'm going to solve for F. I'm going to divide both sides by 0.2165. So 38 divided by 0.2165 is 175.5 newtons. So they're going to have to exert a force of 175.5 newtons on that wrench, which seems like a lot to me, but I don't know. I haven't worked on spark plugs, so. And this, if you note the direction here, okay, as you pull on the wrench to tighten this, you're going to be pulling in a clockwise direction. So this is going to be a negative direction. Okay. Remember, torque has got direction because force has got a direction, and that direction is either clockwise or counterclockwise. Okay. More in the next video.